So this week we're doing freezing and melting points in lab. I'm sure we all know what freezing and melting is, and we've observed it with water and things like that. But let's take a close look at what we're going to see in lab and a little bit closer look at it from a scientific perspective. All right, there's three main phases of matter: solid, liquid, and gas. And we know certain things about each of these, right? We know a solid is rigid. It's got a fixed shape and volume. It doesn't change its shape unless we provide some physical force to it. It's not compressible. The atoms are as close to one another, or about as close to one another as we can get. So that means we can't squish it down any farther, so it's not compressible. Liquids, on the other hand, are not rigid, and they have no fixed shape. They'll take the shape of the bottom of the container they're in, right? Or whatever volume they have, they'll fill that volume of the container. It has a fixed volume. If you dump liquid from one container to another, the volume doesn't change. And again, the molecules or atoms are really close together still. Not very much unlike the solid, but so they're not compressible. We can't make it a smaller volume. And then we have gases. Gases are a little different. Gases are not rigid. They have no fixed volume. They have no fixed shape. And they're compressible. So if I take a gas from one container and put it into another container, it will fill that container. All right? So the volume is going to change depending on the container it's in. The shape is going to change depending on the container it's in. And because the atoms are or molecules are so far apart, we can compress it. That's why we compress gases and such. We can get them closer together and still have them remain a gas. All right, so what's happening to go from a solid to a liquid to a gas, or vice versa? Well, they're transitions. They're called phase changes. Right? To go from a solid to a liquid, it's called melting. You know, liquid to solid is freezing. So red implies you have to increase the temperature of the system, and blue is decrease. So to go from a solid to a liquid, I melt it. To go from a liquid to a gas, it's called evaporation. Going back the other way, gas to liquid is condensation, and then liquid to solid is freezing. Okay, so there are situations where we'll go straight from a solid to a gas, and like dry ice or something like that, frozen carbon dioxide will convert straight from a solid to a gas, and that process is called sublimation. And it will go the other way also. Going from a gas to a solid is called deposition. You can see it down there. So what's going on here? What's physically happening? So if I take a look at gases, the atoms are spread apart. The atoms or molecules have enough energy to get away from each other. And the question is, why do they need to get away from each other? Well, there's attractive forces that are pulling these all together. Okay? If they weren't, they would never be a liquid or a solid. If there weren't attractive forces, everything would remain as gases. Actually, everything would remain as atoms, and nothing would exist except atoms. Okay? But there's attractive forces between these things, and in the gas phase, the energy of the molecules is higher than the attractive forces between them, so that they have enough energy to pull apart and overcome the attractive forces completely. All right, as I cool the atoms down, or molecules down, what happens is they lose energy. And when they lose energy, they slow down. When they slow down, the attractive forces start to be important, take over almost. So if I cool it down enough, the attractive forces start holding the atoms or molecules together. All right? At that point, there's still this balance between attractive forces and the energies of the particles, or molecules, or atoms, or whatever you want to call them. Okay, so the atoms can still move around each other, or molecules can still move around each other, but they're really close together because the attractive forces and the energy of the molecules is pretty close together. Right, so if we take more energy out, of the molecules by cooling them. At some point, we get to a point where the energy of the molecules isn't strong enough to pull them apart from the other molecules, and at that point, we have a solid. Okay, so in the solid phase, the attractive forces are much stronger, or are stronger than the energy of the molecules. In the liquid phase, the two are about equal. The energy of the molecules and the attractive forces are about equal, so they're close together, but they can still move around. Okay. In the gas phase, the energy of the molecules, we've added enough heat, enough energy to raise the temperature enough to make the molecules have enough energy to overcome the attractive forces completely. Right? So that's what's going on with each of these. Yeah, so you can see the little arrow I did at the end there, increase in energy of molecules by addition of heat. Probably should have gone from blue to red, but I didn't. I'll fix that. Here's a phase change diagram. So basically what we're doing on the bottom is adding heat. So if I start over here as a solid, the heat added initially goes to warming up the solid. So you can see the temperature is going up. And then at some point, the solid reaches the melting point. At that point, the temperature doesn't change because the energy is converting the solid to a liquid. So there's a balance here between solid and liquid. Okay? So while the system's melting, it starts off mostly as solid, and by the end, it's mostly liquid or all liquid. So it starts off as all solid, and by the end of that, it's all liquid. But you can see that the temperature doesn't change in that short time. All right, so once it all becomes liquid, after it all melts, the energy goes into the heat that you're adding, goes into increasing the temperature of the liquid until the point that it reaches vaporization or evaporation. The temperature at which it boils, basically. Once it boils, it's now going to work to get all of the liquid to gas. So here we've got a balance between liquid and gas. And the temperature won't change until the majority or all the molecules have converted from liquid to gas. And then any energy added, any heat added, is going to increase the temperature of the gas. Okay, obviously if we go backwards and remove energy, the opposite's going to happen. Okay, I cool the gas, it condenses at a constant temperature. I cool the liquid, it freezes at a constant temperature, then I cool the solid. Okay, so we're going to use the freezing point this one, to determine the freezing point of paradichlorobenzene. All right, we're going to take liquid paradichlorobenzene and put it in a cool water bath and let it come and watch the temperature, and then we're going to graph the temperatures and figure out where the freezing point is, because it's going to level off for a little bit. All right, so like I was just saying, when we do the paradichlorobenzene, we're going to make a graph that's got temperature here and time down here. So initially our temperature is going to be pretty high. I think we start at like 65 degrees Celsius. Remember, your thermometer reads to 1 decimal place, and that decimal place is a 0 or a 5 depending on where it is relative to the lines on the thermometer. And then we're going to watch what happens. And we're going to graph points. And what we're going to find is that for a little while, it's going to stay pretty constant. It may go up and down a little bit, but it'll stay pretty constant. And they'll start dropping again. Okay, at this point, at this temperature, that's what we're going to call the freezing point. That's where all of the liquid is converting to solid. So we're going to graph our data and figure out what temperature that occurs at. Okay, so that's what we're going to do for the paradichlorobenzene, the first part. The second part is we're going to measure melting point, and we're going to do it kind of in the opposite direction. We're going to take a solid, and we're going to take a capillary tube, a thin, narrow tube that's got a hole in the top and is sealed at the bottom. Okay, and we're going to put a little bit of solid in. Basically, we're going to take the capillary tube and smash the open end into into the powder that we have, and we're going to tap on it, and the powder is going to end up in the bottom. We're going to strap this to a thermometer. We're going to put it in some water, and we're going to heat the water. Okay, we're going to watch our solid. When it first starts to melt, when you first see the crystals starting to move around a little bit, you're going to record the temperature. And then you're going to keep watching. And what you're going to see is it's going to melt, and then all of the solid will have converted to liquid. And just at that temperature, just at that point, you want to read the temperature again. So let's say I'm watching my solid and I start to see that it starts to melt. I start seeing the crystals move around a little bit at 46.5 degrees Celsius. Right? And then I watch some more, and all the solid's gone at 51.0 degrees Celsius. Okay, so I am going to, when we record our melting points, we're going to record that range from when it first starts to melt to when all the solid is converted to liquid. And for our melting point, we're going to do 2 trials. The first trial, so we're going to do biphenyl as one thing, and then we're going to do an unknown. Okay, so for each of those, we're going to do 2 trials. So for the first trial, what we're going to do is heat the water kind of as fast as we can with our Bunsen burner, and we're going to get a rough idea of where the melting point is, and then we're going to come back and we're going to do it more carefully. We're going to heat it up, but we're going to heat it up to just below where our melting point, our rough melting point was, and we're going to slowly heat it from there to try to make our range as narrow as possible. All right, and then we'll do that for an unknown, and then we'll be done with this lab. So this is your introduction. This is what we're doing. We're doing phase changes. Melting point and freezing point are going to be the same temperature. So if I take water, the melting point and the freezing point of water are the same thing. It's just coming from 2 different directions. Melting is solid to liquid, freezing is liquid to solid. Okay, we're back in the lab today to do freezing points and melting points. And freezing point and melting point of a compound is the same at the same temperature, right? So if we have water and ice, if I take water and I cool it down to the point that it becomes ice, under atmospheric conditions, it will become ice at 0 degrees Celsius, 32 degrees Fahrenheit. And if I take ice and I heat it up, it'll become water at 0 degrees Celsius or 32 Fahrenheit. Okay, so the freezing point and melting point are basically the same thing, except they're coming from two directions. Freezing point means that you're going from a liquid to a solid, and melting point means that you're going from a solid to a liquid. Okay? Freezing point and melting point are physical properties, meaning that I'm not changing the chemical at all, I'm just changing its state, if it's a solid, liquid, or gas. All right, so if I take ice and I melt it, ice is just frozen water. If I melt it, it's still water, it's now liquid water. Okay, so freezing points and melting points, boiling points, are all just physical changes. I don't change the chemical structure, I don't make a new compound, still the same thing, it's just in a different state. Okay, so today we're going to look at 3 different things. The first is we're going to be given some paradichlorobenzene in a pretty large test tube, and we're going to melt the paradichlorobenzene, and then we're going to put it in a cool water bath, and we're going to watch as it crystallizes, as it freezes. So we're going to determine the freezing point of paradichlorobenzene, and we're going to do 2 trials of this. We're going to cool it down and take temperature every 30 seconds, and then we're going to melt it again and do it again. Okay? So we're going to get the freezing point of paradichlorobenzene. And then we're going to do 2 different things, get the melting points of 2 different compounds. Biphenyl, it's a white solid. I think its melting point's about 70 degrees Celsius. So we'll get the melting point of this. And then we have to get an unknown, and I've got a collection of unknowns here, and we'll get the melting point of these. All right? So that's the plan today. So let's get started. So for all of our work today, we're going to use a ring stand that you can see we've got the stand here and we've got a ring on it. I'm going to put a wire gauze on the ring so that I can simply put a beaker or something on that wire gauze safely, and I can heat the water using a Bunsen burner underneath. Okay, so we're going to do this for all three things we have to do today. For the peridichlorobenzene, we're going to heat the water to about 40 degrees, and then we're going to stop. And for the melting points, we're going to heat the water until the sample melts. Okay? We'll be using a thermometer, and we're going to use what's called a split stopper. So our stopper here, it's got a hole in it, but then it's cut. And what that does is allow me to open it up, and put a thermometer in there really easily, without having to try to force it just simply into the hole. I can just open up the split and I get it around there. Okay, so we've got that, and then we've got a clamp up top here that will hold the thermometer in our water bath. Okay, so let's move on to the freezing point of peridichlorobenzene. Okay, so we're going to do our freezing point of peridichlorobenzene first. We got to do 2 trials. Basically, what it tells us to do is take about 300 milliliters of distilled water in a 400 milliliter beaker. And we're going to heat this. I'm going to add a little bit more water to that just to get it to about 300. Okay. And we're going to heat this to about 40 degrees. And then we're going to get our sample that's over in the hood that's melted at about 90 degrees, and we're going to put them together. And then we're going to take readings every 30 seconds of the temperature and what the sample looks like, so that we can get a nice curve for our freezing point. All right, so I need to get this to 40 degrees. So I'm going to put the Bunsen burner under it. Let's look at the temperature right now real quick to see where we are. And it's about, right now it's about 23 degrees. So we're going to give it a couple minutes here, let that heat up a little bit, and then we're going to get our sample, put it in there, and go to it. Remember, you want, when you're taking the temperature of the water, you want it somewhere in the middle of the water, so you get, because if you're on the bottom, it's a lot hotter, because that's where the Bunsen burner, that's where the heat's coming from. If you're on the top, it's a lot cooler. So somewhere in the middle, just to give you a good measure of the temperature. And we're looking right now about 29 degrees. So we got a little bit to go. 30. Another 10 degrees, and then we can go get our sample and get going. Give it a couple more minutes. Moving on up. We're at 35. $37. 38. I'm going to take the heater out, the Bunsen burner out. Make sure that that's going to get to 40. with all the heat in there and the glass, it should. About 40. Okay, so now I'm going to go get my sample and we'll get set up to take readings. Alright, so with our trials here, with both the freezing and the melting points, I'm going to put this on a split screen. So you're going to be able to see the sample and the thermometer at the same time, and be able to read the thermometer and actually see the sample at the same time. If I want to try to get both at the same time on the same camera, you're not going to be able to see either very well. Okay, so I've got two cameras here, and we'll do it on a split screen. So when you're doing the freezing point, you're going to need to read every 30 seconds and make an observation on how the sample looks at each 30-second increment. So you'll be able to see both and do both. And then for the melting points, you're going to need to watch when the sample first starts to melt and take a reading, and then when it's all liquid and take another reading. Okay, so the melting points are going to be a range when it first starts to melt, so when it's all liquid. So you'll need to take both those, and it'll be a lot easier if you're able to see the sample and the thermometer at the same time. Okay, remember you're reading the thermometer to 1 decimal, and that decimal is either going to be a 0 or a 5. 0 if it's close to one of the lines, 5 if it's in between the lines. All right, so let's get going. Okay, so I've got my sample. I'm going to put it in the clamp here, and I've got my 40-degree water ready to go. Okay, so it tells us we need to start taking readings at 60 degrees. So I'm going to put my, let's zoom in a little bit here and see if we can get somewhere close to it without doing that. Okay, so we can see our temperature. So I'm going to drop it in the water. Once it hits 65, we need to start taking readings, and we need to take readings every 30 seconds for basically 30 minutes. Okay, so you can see that we're still above 60 degrees. See a little crystallization, looks like it's occurring. Oh, there you go, 65. So start. Every 30 seconds you need to be taking a reading. Remember, you should have 1 decimal place. It should be a 0 or a 5. Okay, and with each time that you take a reading, you should be noting what the sample looks like. All right, I'm just going to let you do it. I'm not going to make any more comments. 30 minutes. So that last one, obviously, the curve started going down quite a ways before 30 minutes, so we didn't have to run the whole 30 minutes. So you could see it plateau, you know, it cooled down, plateaued, and then dropped again. So that's all we'll do. And then we'll start the second trial, and obviously I don't think that's going to need 30 minutes either. So we'll just go with what time it needs, and we see that drop and it start cooling down again. And we'll stop at that point. All right. So let's get to trial number 2. All right. So while that's melting over there, I want to make sure my water's at 40 degrees, right? Because that's what we need to start it at. And it looks like. A little bit low, so we're going to put our Bunsen burner over here and let it heat up a little bit. Alright, let's check it again. I don't think it was going to take very long. It's just hanging a little bit below 30. Here, we're right about 40, so we'll stop it there and then we'll wait for the sample to melt. And I'm going to put it in the clamp here. And remember, once it hits 65 degrees, we're going to start taking readings. And then we're going to take a reading every 30 seconds. For 30 minutes. And we're going to note how it looks. Alright, so you can see it's still above 65. Here it comes. All right. 65. Start taking. All right. So every 30 seconds. So it looks like 20 minutes was probably enough because it definitely went through the plateau and is now cooling again. So we're going to stop it here. So we're going to take our sample and put it back in the hot water because the thermometer is definitely stuck in there right now. So we're going to melt it and then get the thermometer out and put it away. Okay, so now that we're done with the paradichlorobenzene and getting the data for its freezing point, we now have to go to our biphenyl and determining its melting point. And to do that, we're going to put the biphenyl in what's called a capillary tube. And a capillary tube is simply a pretty small glass tube. And in this case, there you go, let me show you. So we've got a little glass tube here. And in this case, you can see maybe one end is sealed and one end, the other end is open. Okay? And what I'm going to do is put the open end into the biphenyl and kind of push it down in there a little bit so I get some of the biphenyl into the end of the open tube. So if I open up the biphenyl and just kind of smash down the tube into the biphenyl, we can see that there's some of the white powder in the end of the tube. Now I'm just going to flip the tube over because I want the biphenyl in the closed end of the tube. I'm just going to tap it on the countertop. Okay, and what you'll see now is that the biphenyl is now at the bottom of the tube. Okay, and I have to do this twice because I need 2 samples of biphenyl because we're going to be measuring 2 trials. So I'm just going to do this again. And tap it down. And you don't need very much, just about a little bit, just so we can see it when we're watching it melt. Right? So our 2 samples, I got a little bit more than one of them. Our 2 samples are ready to go. And now what I'm going to do is attach them to a thermometer. Alright, so I have my 2 samples of biphenyl and I have a thermometer. So what I want to do, one at a time, I'm going to attach the biphenyl to the thermometer so that, let me show you, so that the biphenyl is sitting right next to the bulb of the thermometer. The bulb of the thermometer is where the temperature is read. Okay? Whatever is going on in that area of the thermometer is where the thermometer is reading the temperature. As that heats up, the liquid gets pushed, expands and gets pushed up the tube. And that's how we, and wherever it ends up, that's how we read it. Okay, so what I want to do, what I've got is a couple small little rubber bands here. I'm just going to slide over the tube, over the thermometer in the tube. Let me do 2 of them just to make it a little bit more stable. Okay. So now you can see that the biphenyl, the capillary tube with the biphenyl in it is sitting right next to the bulb. Okay. So now I'm going to put this in a beaker of water, and then I'm going to heat the water and watch it as it melts. Okay, what you can see we've done is we got our Bunsen burner ready to go. We have our water bath ready to go. Our sample is attached to our thermometer and it's in the water bath. You can see that it's not touching the bottom or the sides of the glass. It's completely in the water, kind of right in the middle of the water bath. So now what we're going to do is we're going to heat the water using the Bunsen burner. And we're going to watch the temperature go up. So I'm going to do is light this so you can see that, and then I'm going to focus on the thermometer, and I'll have another camera watching the sample. And what you want to do is get a range of temperatures. Okay, we're going to heat this really quickly so you get some idea where it goes, but you want to watch it so when you first start seeing it melting, you need to write the temperature down, and then when it's all gone, when it's all converted to liquid, you need to write the temperature down. Okay? When we do melting points, we do ranges. When it first starts to melt to when it stops melting. Or not when it stops melting, when it's all melted. Okay, so I'm going to light the gas here. There we go. And we're just going to let it heat up. You can see the condensation on the water already. Kind of, there we go. You don't really need to see the flame. You can see it's a bit condensing on there, and then that, as the water heats up, will disappear, and we'll have a better view of the sample. All right, so I'm going to zoom you into the thermometer so you can watch that. Alright, so we're just starting to heat the water. Right now it's reading about 26 or 7 degrees. And we know the melting point's at about 70, so we got a little bit to go. Alright, the water's already up to about 33 degrees. And we can see that there's no melting yet. Remember, we're doing a range here, so we're going to want to get the temperature when it first starts to melt, and you'll be able to see it when you see the crystals start to move around a little bit. And then we want to get the temperature when it's all melted. Also, remember the temperature we're reading to half a degree, right? So remember the thermometer, we're going to read 1 decimal, and that decimal is either going to be a 0 or a 5, depending if it's right on a line or near a line or between 2 lines. Okay? We're pushing up to about 40 here, so we're getting there. Okay, we're moving up about 43 right now. So in a little bit we should be able to see it on our camera on the thermometer. See, it's still all crystalline. Okay, we're getting up a couple degrees below 50, so we're heating up really quickly. All right, Alright, we're above 50 now, so about 53, 54, so we should see it come into the camera here in a second, or maybe a little bit more in a second, sorry. 55. Alright, so you can just see it inching under the camera there. And everything's still solid in the tube. Okay, we moved above 60, so we should be about 65. We should start watching really good. Pushing above 65, so let's keep an eye on those crystals. You'll start seeing some moisture form when it first starts to melt, and you want that temperature when you first start seeing some moisture in there. Oh, you're starting to see it melt. There you go. So you should bring the temperature down now. You're looking for when it's all liquid. Still a little bit of solid in there. Okay, it's all liquid right there. Okay, so those are your two temperatures, when it first starts and then when it ends. When it's all liquid. Okay, so we got a pretty big range there. So with our next sample, we're going to try to get that range a little bit smaller by, I'm going to slow the heating down. When we get to about 65, I'm going to slow the heating down. Okay, we're back with our second trial. And what I did was, since that water was hot enough to melt the sample, the biphenyl, what I did was dump about half of that hot water out and added cold water. So now the temperature of our water is actually about 47 degrees. So what I'm going to do is heat that up to about 65, and then I'm going to slow down the heating. And what I want to do, or what we want to do, is get a better range, meaning we want to get, that first range was kind of big. So what we want to do this time is try to narrow that range, get a better, a smaller range, so we get a better idea of exactly kind of where it melts. Right, so we're running just below 50 right now, so we'll let it heat a little bit here, and then we'll come back then we will slow the heating down once we get up above 60. Alright, we're just going above 50 right now. Okay, above 55 now, so let it get above 60, and then we're going to slow down the heating a bit. And we can see it coming on the thermometer We will read that on the camera now. So we're moving up to about 63, 64. So I'm going to slow that down a little bit. So I'm going to just remove the heat a little bit and see if there's enough heat still in the beaker to take that water up a little bit. You seeing any melting yet? It doesn't look like it. I'm going to tap this to get rid of some of those bubbles. Trying to knock some of the bubbles off the... Okay, so we're still going up in temperature, so we want to watch our crystals there. So we're moving up to about 67.5. Might have to heat it a little bit, so I'm going to put the heat back on there just a little bit. See if we can push that temperature up a little bit. I'm going to take it out. Didn't do much. Let's do that again. Well, looks like things are starting to melt in there. And still working on it. Looks like they're all gone. That's a pretty good melt. Nice. So we got a much better range that time just by slowing that temperature down. So there you go. That's the biphenyl. So now we need to go do our unknowns. Alright, so we've got our unknown here, and let's see if we can see this. It's unknown number 3, and we got to prep 2 samples of that using the capillary tubes. So let me get one here, and we'll prep one and then the other. So again, we're just going to push the capillary tube into the sample. The opened end, right, the closed end, we're going to... well, nothing's going to go in the closed end, so then we're just going to tap it. Do that a couple times. We can see, bring it up here, that our capillary tube has some sample in the end of it. That's the closed end right there. Okay. So we're going to do a second one of those real quick, and then we'll have our 2 samples that we need for the melting point of an unknown. And actually that one looks pretty good. You can see that it's got a little bit in the end of it there. That's all we need. Alright, so those are set. Let's go get their melting points. Again, we're looking for a range of those, right, for the melting point. We're looking for when they first start to melt, and then when they, when it's all liquid. All right, so I've got unknown number 3 here, and we're going to put it in the bath, and see if we can get a decent reading, decent melting reading here. sure everything's set up here okay. Alright, so I think I'm set up. Oh, gotta zoom in and back out and go in. Okay, so you can see we're somewhere between 20 and 25 right now, so I'm going to get the Bunsen burner going. And since this is trial one, we're going to do it pretty quickly. Just trying to figure out about where it melts. There we go, Bunsen burner going. And as that goes up, I will zoom in a little bit. It's fogging up a little bit, that'll clear up. There we go. Alright, so again, we're looking for a range, so we're looking for when it just first starts to melt, get a reading, and then when it's all gone. So we're going to have a range. Temperature's starting to rise a little bit. I'm going to zoom in. Take just a little bit. Right, moving to about 35. Still no signs of melting. Right, so you can figure this out. When it first starts to melt, you should write down the temperature, and then when it's all liquid, you should write down the temperature. camera just a little bit. Right, so I'm going to stop the heating just for a second so I can adjust the camera so we can get a kind of a better angle at the thermometer, so we're not there we go. Put the heat back on there. Bunsen burner back underneath. Hopefully you didn't miss that. If you did, you got to go back and do it again. Rewind, which is good because if you're in lab, you just have to do it again. So I'm going to take that one off and put a second sample on there, and we're going to do it again and try to get a better range. Alright, here's our unknown number 3, the second trial. And this trial we're going to try to be a little bit more accurate, so we're going to try to get a narrower range of our melting point. So we're going to heat it up to about 60 and then we'll slow down. Alright, so the thermometer I've just got kind of set about where we need it, so you're probably not going to see it for a couple minutes here, or the alcohol you're not going to see for a couple minutes here. But you can see in the other camera that we definitely have a solid. So what I did again was I took some of that water out because it was too hot. If we had put our sample in that hot water, it would just melted. I poured some of it out, not all of it. I added some cold water to cool it down a bit. And it's looking like it's about 40 degrees right now, the water temperature. So 40 degrees Celsius, right? These temperature measurements are in Celsius. We're moving up to about 50, so From the camera on the thermometer, you should start just about see the red alcohol coming into frame, and it just did. So we'll let it go for a little bit longer, and then we're going to kind of slow it down a bit. Alright, so we're coming up to 60. So once we hit a little bit above 60, I'm going to pull it out of there, the Bunsen burner, and let it kind of see if it'll heat a little bit without the Bunsen burner, because of all the residual heat sitting around. We're at 63. Not seeing any melting yet. $65. So we'll put the Bunsen burner back in a little bit. Heat it up a little bit more. Take it out. A little bit more. Take it out again. Looks like it did it pretty well. Alright, there we go. Give us a couple ranges. Hopefully that second one was better than the first. Okay, now we just got to clean up. And we'll get to that in a second. Alright, so as we wait for things to cool, remember all that stuff is going to still be hot. All the metal on the ring stand, the water, the glass, that's all going to still be hot. So we're going to let that cool a bit before we even touch it. Because it's hard to tell the difference between hot, cold metal or glass. They kind of look the same. So what we need to do now is the capillary tubes that we use. All these guys. Okay, we're going to come over to our by our sink here, and we've got this brown container. Okay, and you can see that it's broken glass only, and that's where these go. So I'm just going to drop those in there. Ooh, put them all in there and not drop them all over the place. Grab that one. And then what happens to that is that all goes to a broken glass container, which is a big cardboard box, or not big, it's a cardboard container that then goes in the trash. It's just to keep people from cutting themselves, like putting it in the trash, where somebody might come and empty the trash and grab something out of there. We don't want that. So all glass goes into one of these, and then they get emptied into a bigger container that ends up in the dumpster. All right, and that's about it. We're just going to let everything cool down, put it away, and be done with melting point, freezing point lab.